Hi, my name is Braden Massey.
I'm Matthew Rostad.
And I'm Jarek Trombley.
And we make up the Microwave Filter Tuner project for final year project at the University of Regina. So the Microwave Filter Tuner project is basically based on our client's requirements. Dr. Paulo Forge at the University of Regina. He's basically looking to replace the labor-intensive, very manual way of tuning microwave filters. Now they've been developing an algorithm that tells them how much they need to rotate each screw on a given microwave filter. But they want to remove the human, the manual aspect of the process by having a machine locate the screws, line up with the screws, and rotate them accordingly and accurately and consistently, further allowing them to improve their algorithm. So just going over what I did in the project, I did the mechanical subsystem design, as well as I did the VDS or visual display subsystem, as well as a portion of the visual identification subsystem, so the wide angle camera mappings, that's our initial mapping.
So what I worked on the project is I did the motor control subsystem for the X, Y, and Z movements. I did part of the visual identification system, including the lighting and the zoom camera. I did the communications between the PC and the STM, as well as the communications between our Python program and the university's MATLAB program.
And I was directly involved with the PHY portion of the motor control subsystem, including the homing of that system as well. I was also a part of assembling and designing the power supply subsystem for our machine. And then lastly, the GUI interface that you will see an interface with tuning the filter.
Now let's talk about the mechanical subsystem. So this is one of my aspects of the project. So looking at the machine first, we designed it using a CNC style machine. So we went to OpenBuild. It's a company that specializes in creating custom components that you can combine together to make a CNC style machine. So we did this by using SolidWorks to put all these parts together from their SolidWorks library, in addition to producing our own 3D printed parts. Now there's about 25 plus unique 3D printed parts on the machine, and over 90 3D printed parts total on the machine. So if you come a little closer here, start at the front. Basically the mechanical system consists of 5 different elements. The first is the bed and frame. So the bed and frame is essential for obviously putting our filter down, like this one for instance, setting it down, and then having some means of clamping it down. The next stage of the mechanical was our gantry system. So this is essential for our movement, and it's why we sourced it from OpenBuilds instead of producing it ourselves. So basically this allows us to move in the X, Y, and Z axes. And this is essential, obviously, for reaching our goal because we do have to move in 3 degrees of motion. Additionally, we have the 4th degree of motion, which is our phi axis. So this allows us to rotate the screws accordingly, as well as line up with the screws accordingly. Now, there's a few things going on with the mechanical. Starting with the screwdriver module, is when we contact a screw, we're going to move upwards until we've engaged this limit switch. So this gives us a reasonable amount of force, between 15 and 30 newtons of force onto the screwdriver, which is in the expected range of a screwdriver. This is essential, obviously, for applying force so we're not slipping within the screw itself. As well, this travel allows us to move up and down while we screw in a screw or screw out a screw. So it gives us some natural travel that you would have with a human. On the X and Y axes, we have a few key things to note. We have an anti-backlash nut. So this again improves our accuracy. We don't have any backlash for obvious reasons, and it keeps it within a reasonable range. Now, the mechanical is an extremely accurate portion of the project. The accuracy from the things actually come further with the electrical and eventually the software. But mechanically, it's more accurate than we could ever use or need. This whole thing obviously has been designed to support that 10-inch by 10-inch filter requirement. That's essential, obviously, once again, with our requirements, the 10-inch by 10-inch. And with that, we have our limits, which is obviously restricting our actual movement. Coming to the back here, we've all conveniently mounted the electronics in the back here. We'll further elaborate on that later, but effectively it's a piece of plexiglass bolted on, and then a secondary piece for protection. The motors coming off the back are NEMA 23s, while we have a NEMA 17 for the screwdriver module and a NEMA 23 for the Z and X axis. Those give us the necessary torque, which we calculated early on in the project, in order to move the machine without any binding and keep that accuracy and torque up. Finally, we have a few more elements like the bed brackets that we've designed, and then the screwdriver module, which we're about to get more elaborate into. Alright, so now I'm just going to give some more explanation on the screwdriver module since it's such an integral part of the mechanical. So looking at it here, the entire thing is mounted on a gantry plate. This gantry plate gives us an up and down vertical motion. The entire Z-axis is mounted on the X-axis right here, as well. So that's our combination there. This motor gives us the ability to move up and down. So when we actually meet the screwdriver, we're going to make contact with the screw and we're going to push it up and engage that limit switch. Now there's a few key brackets here. We have basically two shafts happening. So we have the motor shaft of the NEMA 17. This goes into a flexible coupler. The flexible coupler gives that ability to basically misalignments are solved instantly, or at least relatively well. And then on top of that, we have our screwdriver shaft. So this is a machine screwdriver shaft. So this is about 15 centimeters long, combines into the flexible coupling, and then has a flat portion here to avoid slippage. On this, we mount our encoder, which Jared will further elaborate on. And then we have our optical sensor here. And of course, we have our zoom camera right here. So this is another custom bracket like this one as well, and this one and this one. These two brackets have bearings in them. They have 6mm bearings to ensure the straightness and the lack of slop. And then just on the back here, we have the rear camera, or our wide angle camera, what is used for mapping. So now we're going to talk about our VDS system, or visual display subsystem. This is integral for doing things like our errors and our statuses. So we want to make sure that our users know exactly what's going on with the machine, as well as when they encounter some sort of situation we've accounted for. So if you take a look here, we have our LCD. So we have our 4-line LCD display. So our first line is for branding purposes, so the University of Regina. Our second line is the version of the machine, as well as its shorthand name of MFT. We have our third line is our status. So that'll update, when we're moving phi, when we're moving X, moving Y, homing, all those situations. And finally, the fourth line only occurs when we experience an error. So such errors include, a bad G-code command, or repeated bad G-code commands, or hitting a limit switch, or unable to home the phi axis, and so on. So we're just going to get a quick demonstration. So right now we see it's disconnected. So Matt's going to send a command here that's going to connect it. We basically have a two-way response on that Matt will further discuss later. So now we see it's gone ready. So we have our three LEDs here, that are going to indicate that. So a green LED is when we're in the ready state. So we're ready to receive a command. The yellow LED is in the event we receive what we call a recoverable error. So that might be receiving a single bad G-code error. And then finally, we have our fatal errors, our red errors. And those happen basically like hitting a limit switch. This machine stops dead in its tracks, no longer can go forward. It requires a manual reset with our stop button. Now, we're just going to do a few movements here to show the statuses. So Matt's going to move the X-axis.
I'm going to move it home.
Move it home, rather, to begin with. So we can see it's now moving X, Y, and Z, or homing, rather, X, Y, and Z, as the machine is doing. And so on. If we go on to moving X, so if Matt moves up somewhere to an X position, so we have our moving X. Now if he moves the Y, moving Y, and moving Z, and we have moving phi, as you can see, it's moving. Now we're going to do a few different errors. So Matt's going to send it a bad G-code. And we're going to see here a G-code error. So we have 3-1. So that's 3 means it's non-critical. 2 is also non-critical. And 1 is just the first error code in that situation with a nice description for the users. As you can see, the yellow or orangish LED has lit up, indicating it's non-fatal, and we don't need a reset at this time. Now, if we go ahead and send repeated bad G-codes, and again, now you can see it's fatal. So we've gone red. This now is not able to recover, rather, so we're going to have to do a full reset. So by powering it off, powering it back on, we're in that initial setting. Now we're going to kind of show some limit switches. So if our limit switches, it's important that our users understand where we were hit and how they can recover from it. So Matt's going to home it real quick here to get us back into speed. Then while moving the X-axis, we're simply going to hit the limit switch preemptively. It's going to think it's hit a limit switch. It's going to enter a fatal error, and then we'll obviously require a reset. And the same thing can happen with each of the limit switches naturally and occur obviously for safety purposes. So we don't have the machine go out of its bounds, grind, bind, whatever the case may be. So Matt's going to move the X-axis here. I hit the limit switch. In our case, we actually implemented the limit switches as recoverable errors, but for future improvements, they're obviously going to be recoverable errors, rather, but right now we consider them a fatal. So we've maintained that same architecture. While it's technically fatal in its current stage, our future improvements would basically have it that it rehomes again and then continues on working. And if it repeatedly hits a limit switch, then it would do it. But that was not currently implemented at this point.
Hey, so I'm Matt. I'm going to talk about our microcontroller and our protoboard. So this is one of the sections I worked on, and one of the first things we had to decide was what microcontroller are we going to use. So we decided we would go with an STM because that's what we're familiar with. And we decided on the same STM boards that we used in the labs because we're familiar with it, it had enough pins, and it met all of the requirements for being able to control the machine. Now, the protoboard itself is effectively just a breakout board for the STM with a few other components on it. So as you can see in the middle here, we have the STM board itself. Over here we have all of the power supply components. That's a 3.3 and a 5 volt recom and linear regulator, as well as a 12 volt recom to control the lighting. Over here we have MOSFETs and relays which control the lighting. Over here we have a USB to serial converter. I'll elaborate on this more, but this effectively allows the PC to communicate with the STM. Now, as you can see, all of these green screw terminals here are how we connect the STM with the rest of the stuff on the machine. So we have the LCD stuff down here, the limit switches, and then all of the motor control pins here.
So next I'll talk about our power supply subsystem. So it has a couple components. Our main component is going to be this power supply here. So it's running off of 120 mains. So it's 24 volt power supply rated at 14 amps is how much our current we can supply to all of our motors. Now that's spec'd a little bit higher than we needed. Of course, when we're looking and sourcing our power supplies, we found that this was just the best cost for what it was able to supply. So we didn't need quite the 14 amps, but we were kind of close at around the 12 to 13 amps. So still enough room for that. I'll kind of touch about the little bit of isolation here between the protoboard and our power supply. So we have the fuse right there. So if we ever draw more current than we're expecting, that's going to isolate our main circuitry there. We have part of the power supply subsystem that Matt kind of touched about just a little bit ago would be these recoms here. So we have a 12 volt switching regulator, our 5 volt switching regulator, and we have a linear power regulator, which is our 3.3 volts for digital logic. Kind of all part of the power supply subsystem would be kind of the wiring and the management scheme that we chose. So definitely wanted to make sure that we had lots of strain relief so that anything was to be snugged or tagged incidentally. It wasn't going to just come and fall apart off the machine. So our power supply has 2 points here of strain relief. Lots of strain relief throughout the rest of the wire management. We chose to use kind of a spiral plastic loom here that works great for moving X and Y positions, which we can kind of illustrate kind of a simple Y movement. So as you can see, the spiral loom works great in this case for managing and encasing the wires for the rest of the motors, the lighting, and limit switches. On the side here, we also have a kill switch. So this is going to kill power, not to the power supply, but to the system itself in the event that something has gone critically wrong. So we'll illustrate that here by just homing the machine, and we should kill it and it should stop right away. So that's effectively done exactly what we said it would. So now that has stopped the machine. If we turn it back on, it's essentially stopped in its place.
So now I'm going to talk about a very important part of this machine, which is the motor driving subsystem. So to start with, we had to select our stepper drivers back here. These obviously had to be able to support the current from these motors, which was up to 3 amps is what these motors can draw. They had to have micro-stepping ability, and they had to be able to select the current, since we do have different sized motors on here that have different current requirements. So we ended up selecting the TB6600s. These are a relatively low-cost stepper driver, which was good for us. They have micro-stepping down to 1/16. We only end up using 1/4 micro-stepping, but it has the ability to go more precise. They support up to 3.5 amps, which was more than enough for our stepper motors. Then at the top here, it's very easy to adjust with just a few little switches. And we actually 3D printed these covers to prevent anyone from flicking these switches once the settings are dialed in. Yeah, so these stepper drivers are of course controlled by the STM. And thankfully there's nothing fancy that had to be done. You could just connect the STM directly up to the inputs on these stepper drivers. And of course each motor has its own stepper driver. So these two control the Y motors. This one controls the X, this one controls the Z, and this one controls the Phi that Jarrett will talk about more. So each motor gets its own dedicated stepper driver. Now, these of course allow the axes to move back and forth. So one of the first things we had to do was figure out how we're going to make this thing go into its home position. So we decided the home position would be in this corner here with the Z all the way at the top. Now, when it's coming into home, it's going to come in, hit the limit switch, and then bounce off the limit switch, and slowly come back, hit the limit switch, and then move off. And that's going to allow us to precisely be at the same point every single time. So now we'll demonstrate it finding its home position. So it's going to start with homing the Z, and then it's going to home the X, so it hits the limit switch, bounces off, and then slowly contacts it again. Finally, we're going to home the Y. And now we can just demonstrate moving the Y axis. If you want to do move it like 100 or something. So as you can see, when it moves, we're not just simply, jerking it right up to max speed. It has an acceleration curve, and then it coasts for a certain period of time, and then it decelerates. So those are all parameters that can be changed, but we dialed it in to have close to the maximum speed that we could have, so it'll accelerate and then coast and then decelerate, and that makes sure that we don't skip any steps. We're not putting too much strain on the motor or any of the mechanical.
So another part of the motor control subsystem that's quite important is the Phi axis. So the Phi axis is being run off of this NEMA 17 motor that is connected by this flexible coupling, and also attached to the screwdriver shank is our homing encoder. So their rotational encoder is going to help it home to its correct position, which is going to be at a 90-degree angle. Part of the pre-tuning process is that each screw is set to a 90-degree, which then after each screw is turned, the system itself is going to keep track of its rotation. Matt's going to explain a little bit more of that as part of the back end of our computer software. So yes, essentially when we have the motor, it's going to line up with the screw. Part of the visual system is going to line up with that. Our Phi system is just going to rotate a specific degree. So it has a very fine accuracy. At 1/16 microstepping, we're able to rotate as small as 0.1125 of a degree. With our error, we have 0.25% error for each degree. So if we're to turn a degree, it's only going to be off by as low as 0.25%, which is quite good. We were aiming for at least 1% error, which we've achieved that in this particular system. So I guess we'll demonstrate it rotating at 90 degrees, and then we can try home it afterwards just to illustrate that. So we rotated 90, and then we'll home the encoder. So now it is homed, and it is at a 90-degree orientation for our screws to properly align. Up next, we'll show you our GUI for the microwave filter tuner. So point out a couple things. Just on the left side here, we have our settings. So we'll be able to select the screw. At this time, we only have the 1032 Phillips screw programmed into the system. Future improvements would be to implement multiple screws, so you can not confine your option to just one single screw. We have wide angle and zoom detection sensitivity, so depending on any additional factors, you may need to alter these values so that it is detecting the screw properly. We have our COM ports, so just selecting which ports is pretty essential to be compatible on any machine. We have our tune and tighten button. So our tighten button at this time is not implemented, so that is also another future improvement that we would like to add at some point. It wasn't feasible in our current scope, but we have that simply there for the time being. Our refresh and cancel button don't do anything at this time either, but essentially another feature improvement would be to at some point cancel the process. We do have an emergency stop button that can serve as the same process, but as a software implementation, we would like to have some way of controlling and canceling a process in the middle of a tune. Here we have the ability to enter in single G-code commands, so you'll be able to user will be able to enter in a command and send the command. We'll fire that command off to the system itself. Up here you'll see some images. Now again, these images are being supplied from the system itself. The original intent was to have these images refreshed after each snapshot. Again, that isn't working as intended, and it would be a future improvement to have these images show up. Essentially, they show up after the tuning process is complete, and then this output response would then be supplied by the MATLAB algorithm that would show us the output filter response once it's tuned. So that essentially, in a nutshell, guys, is our filter tuner GUI, and Matt can talk a little bit more about the back-end process.
So now I'm going to talk about the OpenCV aspect, or the computer vision aspect of our project. Now that aspect allows us to map the position of the screws and just figure out where these screws are on the bed. So there's two cameras that we have on the machine. One of them back here is a wide angle camera. And then up here we have the zoom camera. Now both of these cameras use the same 5 megapixel sensor. The only difference is the lens. This one has a very wide angle lens. The zoom camera, of course, has a very zoomed in lens, of course. Now the purpose of these two cameras, the wide angle camera will get us an approximate map of all the screws. So it's going to be able to see every single screw that's on here and the approximate location within a couple of millimeters. Now when we want to tune a specific screw, we will move so the zoom camera is directly over top of that screw, and then we'll be able to very precisely know, generally within 1/10 of a millimeter, know where that screw is located. Then we can come in with the screwdriver and rotate it. Now we're going to give a demonstration of both of these cameras during the throughout thorough demonstration, but for now that's a good overview of what those do. So now we're going to just do an overall demonstration of the machine tuning a filter from start to finish. Now, of course, we don't have Paul's algorithm yet, but we have a robust communication system between our program and Paul's program in MATLAB. So once we do get his program, there should be no issue with communication between the two. So now let's jump into the physical filter itself. This is one of the analogs we have in the ANT configuration. And we have these brass inserts here, which allow the screws to turn properly. Now for this demonstration, we actually have a variety of different screw types. So they're all stainless steel screws, and some of them are pan heads, some of them are flat heads, some are stainless steel, and then some are painted matte black, and all of these will actually work just fine with our algorithm. Now the tape is over top of the filter just because these threaded inserts are round, so the tape just helps with computer vision. And this is something that can be done on a real filter as well. If there's anything on the filter you don't want to be detected with computer vision, you can just simply put tape over it. So now we'll demonstrate the use of these clamps here. They're very simple to just slide into place, and you're able to clamp it down on just 2 corners. And that's enough that the filter will not move at all, so it's stuck in there. Now, as Jared mentioned, part of the pre-tuning process is all these screws have to be set at 90 degrees to start with. Now, of course, when this is actually being used, there's more accurate ways of doing it, but for this demonstration, we'll set them all at 90 degrees. And now we can jump over here to the PC, and we can start the tuning process right away. So as I mentioned, this is our shared tuning file between MATLAB and Python. So it's just simply the screw number and then how much you want it to turn. So 360 degrees, minus 360, so on and so forth. Just tells you how much you want each screw to turn. So now we're going to open up the GUI here. And as you can see, we have our settings over here, our COM ports, and then our tune button. So to start with, we will simply hit the tune button. It's going to begin by homing the machine. which is something that we demonstrated earlier, and it must be homed every time so it knows where 0 is. And now it's going to move into a central position so it can take a wide angle photo. It's going to turn the lights on, take a wide angle photo.
So now we're going to talk about the wide angle portion of this project. Effectively what we're doing here is we're using the hue circles detection function from OpenCV. And as you can see, we've detected the 6 screws. Now we've detected a few other screws, or rather circles, but that's not a big deal for us in this case because we have something called the screw assignment process. So effectively what we're going to do is we're going to go in, we're going to click each individual screw, and we're going to assign it a number. Now this is a paramount step because the algorithm that the University of Regina is using has numbered their screws based off the topology. Naturally, we can't know the topology of a variety of filters reasonably, so we have them simply assign it. This also allows us to filter out the circles. So from there, we hit enter. You can see now that we filtered them out, we only have the screws we want, and this will be the order of our screws, and we'll continue on tuning from here.
Okay, so as Braden was mentioning, we have all of these screws assigned and all the screw numbers assigned. So now we're ready to begin the actual tuning process. It's going to hit enter here, and it's going to start aligning the zoom camera with the very first screw. So the zoom camera is directly over top of that very first screw, and it's going to take a zoomed photograph of it. So now if you come over here, the black line represents the center of the frame, or the center of the camera, and the red line represents the center of the screw. So as you can see, the wide angle camera is very good, but it's not quite perfect, so it's off by just a little bit. And that little bit of offset is what the zoom camera is able to compensate for, which is going to allow us to hit the screw dead on. So now I'm going to hit enter here. It's going to align the screwdriver right over top of the screw, align the phi axis, and now it's going to lower and align with that screw and turn it 360 degrees as specified by the tuning file. Now this process is just going to repeat over and over, so it's going to align the zoom camera with the head of the screw. It's going to take a zoomed photograph, and again there's a small offset, but it's able to compensate for it. So as you can see, it moves down, and just before it reaches the screw, it actually slows down until it contacts this limit switch, and that's how we know that we've aligned with that screw, and we know we've successfully hit it when that limit switch is contacted. Now if that limit switch doesn't get hit in time, then that'll throw an error message indicating that there was no screw. So again, it's going to move down, it's going to rotate, turn that screw, move back up, align with the next one. And it's also worth noting, as mentioned before, that this is working with a variety of screws. So it's working with flathead, panhead, silver, black. It's just working with all types of screws, which is very important, so it's truly a universal filter tuner. Now this is the final screw here, so it's going to align with it. And again, take a zoomed photograph, line up the screwdriver with it, home the encoder, move down, rotate that screw. So now we've effectively tuned this filter to the requirements of what the tuning algorithm told us. Now, of course, in reality, you're not just going to do one quick tuning cycle, you might do another one. So it might send us another tuning file, and then it would repeat that whole process. Now, once it's done, MATLAB is going to send us a tuning file of all zeros. So I'm just going to quickly make one here, just a tuning file where all of them are zeros. Yeah, you don't need to show this. But I'm just going to make a tuning file. They're all going to be zeros. And then that's how it knows to end once they're all zeros. It's going to read that file, and it knows there's no more to tune since all of them are zeros, and we're done. So that's the tuning process complete, all the way from reading the file to taking a wide angle photo, to aligning with each screw, taking a zoom photo, turning each screw the correct amount. And then once MATLAB determines that it's done, it sends all zeros in this tuning file, and then our machine knows it's done and shuts itself off.
All right, finally, let's talk about the testing of the system. So obviously you just saw our filter tuner just tune the ANT analog. But we actually have a few different analogs we've been using to verify that this machine has worked. We have a few different configurations. We have our circular, so we have as close as possible within our reason, if not a little bit closer. And this has a nice configuration of 9 screws. We have our duplexer, the most realistic configurations of screws we have in our collection. And this is based off of a real filters configuration. We have the ANT, as previously mentioned, our easiest version, but definitely keeps the closeness and has the most realistic turning screws. We have what we call the snake. This one is a configuration of 11 screws. And basically this one's a random positions, no real particular pattern to try to mess up the system. And finally, my personal favorite, the Mega. This has our 20 screw requirement as well as our 10 inch by 10 inch filter. And this basically, if we can tune this, we can effectively tune anything within that realm of possibility. And all this combined with our test cases. So for testing, we did a component level testing. So that's testing the motors, it's testing the limit switches, testing the encoder, the mechanical and its individual elements. And then from there, we use that to verify our components work, and we worked our way up to the subsystem testing. So that's things like the visual display subsystem, the motor control subsystem, the power supply subsystem. And then finally, we finish with the ultimate testing, which is our system testing. So that includes running these filters repeatedly to see that we tune it start to finish using every subsystem capable. And we ran hundreds of test cases we produced, and whenever possible, the designer of that subsystem or a chooser of that component was the one not testing. So another person would test to further distance ourselves and remove any biases. So ultimately, that is the microwave filter tuner project, and that's our whole demonstration.